Hello students, welcome to Sri Jayendra's Rank Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 7 of a unit moving charges and magnetism. In today's session we are going to discuss about the Ampere's circuital law. So let's begin with today's class. Now according to the Ampere's circuital law, it says that the line integral of B dot dl taken over the entire closed path of induction in a given perpendicular plane is equal to mu naught times the total current enclosed in the closed path. Yes, please go through one more time. It says that line integral of B dot dl taken over the entire closed path of induction in a given perpendicular plane is equals to mu naught. This is mu naught times the total current enclosed in the closed path. It says the line integral of B dl is equals to mu naught times of I enclosed. So let's understood one by one everything. First, line integral. What does it mean? What does it mean? If I take that this is the square, and if I take a line integral of this, if I take a line integral of this, it would be a, let's suppose this is the square of length L, it's a 4L. Let's say I take a circle, and if I take a line integral of it, it's a 2 pi r. Yes, exactly, you are adding up, every length of your figure. Yes, or you can say you are calculating perimeter. I hope you remember this. Yes, you are calculating perimeter. In the previous cases, that's if you remember the Gauss law in the first unit, moving charge and magnetic moving charges, it's a surface integral. It was there. It was the surface integral. So in the case of surface integral, let's say it's a square of L by L. So if I take a surface integral of this, it's an L square, something like this, it's a R. Yes, if you take a surface integral of this, it's a pi into R square. So this would be the situation, that this is the difference between line integral and surface integral. I hope this is clear. Now what according to the Ampere is that, let's say suppose this is the current carrying element, and this is one of the circular loop, and on the circular loop direction is given like this. Then according to the Ampere, the line integral of this loop, it's a B dot dl is equals to mu naught times of I enclosed. Please do remember this word, that line integral of B dl would be equals to mu naught times of I enclosed. That means I need to write down all those current elements only which have been enclosed by this circular loop. I hope these things are clear. Is it clear? Is it? Great. Now suppose the situation is that, let's suppose this is the circular loop. One of the current element is having direction like this, I1. Another current element is having direction I2, and this is the direction of loop, let's say. So what I need to write is it's a line integral of B dot dl is equals to mu naught times, I need to write down the I1, I need to write down the I2, but which one is positive, which one is negative? How could I take a decision? That which one should be considered as a positive, which one should be considered as a negative? Because as you understand that we are talking about the magnetic field, and when we talk about the magnetic field, it is always a vector quantity, and if it is a vector quantity, we need to respect its magnitude as well as direction. And to respect that, I need to understand that where should I taken it as a positive, where should I taken it as a negative. So let's understood first, and then we will back to this. So this was the situation, this was the loop, this was the I1, and this was the I2, and the direction of the loop. Yes. So what you are going to do is, what you need to do is that use your right hand, use your right hand to find out the directions. Now how you are going to supposed to use it, that curl your right hand fingers, curl your right hand fingers in the direction represents by loop. Curl your right hand fingers in the direction represents by the loop. Then the direction represented by your thumb, the direction represented by your thumb will be, or will, that current element, that current element is positive, and vice versa. Now how to do this? Let's have a practical use of it. It's a line integral of b dot dl, that should be is equals to mu naught times of. Now use your right hand, use your right hand, curl your fingers in the direction as seen by the loop. Yes, it's an anti-clockwise. A loop is saying that it should be in an anti-clockwise direction. So if I make an anti-clockwise, if I make a curling of my fingers in the anti-clockwise direction, then I understood that my thumb will represent, my thumb will represent the outward current as positive, because it is showing in the upward direction. For I2 it is moving in upward direction, for I1 it is moving in downward direction. So this should be plus I2 minus of I1. I hope this is clear. Is it clear? So even in this case, what is the direction? Yes, the direction represents that upward will support, downward will oppose. That means I2 should be a positive one and I1 should be a negative one. I hope this is clear. Is it clear? Is it? Great. Let's have a practice of it. Let's say suppose this is a circular loop and there are certain elements. It's an I1, it's a, let's say I2, it's a I3, it's a I4, and let's say it's an I5. The direction of loop is in this direction, that means it is in clockwise direction. Yes, so you need to do two things. You need to do two things. First, you need to write down line integral of b dl is equals to mu naught times of this. Yes, so first perform this and I will let you know the second task. Yes, first what you need to understand is that when I write this, I used to have I enclosed word with me. That means I am going to write down all those elements only which have been enclosed by the loop. That means I need to write I1, I2 and I3 only. No need to write I4 and I5 because they are not going to contribute it. Yes, so this is when I write I enclose, it's a line integral of b dot dl, that should be is equals to mu naught times of, look at this, a loop is moving in the clockwise direction. So curl your right hand fingers in the clockwise direction. You will find that your thumb will be inside the plane of the paper. So when it is inside the plane of the paper, who will be the positive? Yes, I2, because even I2 is in inside the plane of the paper. So this is plus I2 minus of I1 and minus of I3. Only this 3 would be there. I hope this is clear. But if someone asks that find contribution in magnetic field in this region, yes, then who will contribute to produce magnetic field in this region? So when they ask for the magnetic field contribution in this particular region, I need to write the name of each one, everyone. I1, I2, I3, I4, I5. Yes, this all is going to contribute to develop a magnetic field in this region, because according to the Ampere circuital law or the Biot-Savart law, or now even the Ampere circuital law, when and when current is flowing through conductor, it will produce a magnetic field around it. Yes, so this is even true at this point also. I hope this is clear. Is it clear? Is it clear? Yes. So magnetic field will be contributed by each one, everyone. Again, when and when I need to find out the B net, I'm going to have a vector addition of this magnetic fields, but it is there due to each one. I hope this is clear. Is it clear? Any doubts? Any doubts in this? No? Let's quickly work on the questions. Let's have a look. Suppose this is our loop and we have a current element that this is I1, this is I2, this is the direction. I hope this is visible. Yes, okay. So I need to write down the line integral of B dot dl. What it will do, it's a mu naught times of I enclose. So let name this loops as a first loop and second loop. So if you observe this carefully, you will find that your first loop is moving in the clockwise direction. In the first loop, it is moving in the clockwise direction. And if it is moving in clockwise direction, magnetic field or the magnetic field will be the downward. But here the current element I1 is in upward direction. That means you need to write it as mu naught times of minus of I1. Yes, because it opposite. And in the second loop, the thumb will represent the outside direction, but your current is in downward direction. So this is mu naught multiplied by minus of I1 minus of I2. Yes, is it clear? Is it clear? Are you sure? Great. Now let's work for this question. Do it quickly. Now you understand the situation very well. Yes, this is the situation. Here the I1, I2. Yes, take your time of 30 seconds and do this quickly. Then we are going to check it. Do it fast. Yes, have you done it? Have you? Have you? Okay, let's have a look. It's a line integral of B dl is equals to mu naught times of this. In this, it is the clockwise. Even the current is in downward direction. So this is plus I1 on the second loop. The loop is moving. in the anti-clockwise direction, but current is in inside the plane, so it would be a minus. It's a minus of I2. The third loop is in clockwise, but current is in the outside the plane. It's a minus of I3. The fourth one, loop is in anti-clockwise direction. Loop is in anti-clockwise direction, and current is in inside. So again, this is minus. Yes, minus of I4. In the fifth one, loop is in clockwise direction. So even thumb will represent the inside the plane, and as well as current is showing the same. So this is something like this. Yes. Now suppose someone have asked me, this is I6, this is I7. Should I write this in I enclosed? Should I write them in the I enclosed? No, I am not going to. One thing. Second thing, who will contribute? If they ask, who will contribute to the magnetic field in this region? So if they ask about the magnetic field, my answer should be I1, I2, I3, I4, I5, I6 and I7. This all were there. Who is going to contribute for the same? So from I1 to I7, they are going to contribute to develop a magnetic field in this region. I hope these things are clear. Is it clear? Is it? So do not forget it, that when you need to write I enclosed, you need to write down only those current elements which have been enclosed by the ampere loop. And when you need to write down the magnetic field contribution, then you need to write down all those current elements. Which were there in that region. I hope this is clear. Is it clear? Is it? Great. Now let's look at the applications of Ampere's circuital law. Let's have a look. First, it's a magnetic field due to infinite long thin straight current carrying conductor. Yes, for this we have already derived the relation according to the Biot-Savart law, if you remember. Yes, it was for finite and then we have switched to the infinite. Yes, so we are doing the same thing, but according to the Ampere circuital law. So let's have a look, how should I do this? First, according to the Ampere circuital law, I understood that line integral of B dl is equals to mu naught times of I enclosed. Yes, so if I take any position, if I take a position of this, then element of dl and this magnetic field is in this direction. dl, again it is in this direction. So if I look at the angle between these two, its theta would be a 0 degree, and if its theta is 0 degree, it's a B dl cos 0 degree, that is equals to mu naught into I. Now B is the constant, yes, throughout the circle. It's a B line integral of dl is equals to mu naught times of I. Now according to the dl, as we have discussed in the very first slide, it's a line integral of dl is equals to 2 pi r, and this B into 2 pi r is equals to mu naught into I. So B could be written as mu naught I by 2 pi r in the outside the plane. I hope this is clear. Is it clear? Is it clear? Are you sure? Yes, even when we used to have this according to the Biot-Savart law, have you remembered this? It was something like this, that this is point P, this was the R. We used to have two lines over here. One of the angle was called as the alpha, and the another one, this was called as the beta. So this magnetic field at point P, it is equals to mu naught I by 4 pi r multiplied by sine of alpha plus sine of beta. This is magnetic field at point P, mu naught I by 4 pi r into bracket sine of alpha plus sine of beta. And for infinite length conductor, for infinite length conductor, we are having magnetic field at P will be equals to mu naught I by 4 pi r into bracket this alpha and beta. Both should be a 90 degree when we consider it's an infinite. This is equals to sine 90 degree plus sine 90 degree. It's a 1 plus 1 2. So this is equals to mu naught I by 4 pi r multiplied by 2. So that should be mu naught I by 2 pi r. Yes, it was the same result. It was the same result that we are having this. Yes. So according to the Biot-Savart law as well as according to the Ampere-Circuital law, the relations will be the same. Only the concepts behind it, or we can say a formula behind it, would be the different. So you can use any of them by applying a correct applications. Yes, you need to apply a correct angle and you can go for it. I hope these things are clear. Yes, so this is the first application to find out the magnetic field at a certain point due to straight current carrying wire. Now let's look at the second application. It's a magnetic field due to infinite long solid cylindrical conductor. Yes, let's suppose a current I is flowing through the cylinder and we have chosen 3 points. One of the point is inside the cylinder. Another point, it is on the axis of the cylinder, that means on the surface of the cylinder, sorry, not the axis, surface. And the third, it is the outside the cylinder. So what I need to do is, I understood the simple mathematics. It's a line integral of B dot dl is equals to mu naught times of I enclosed. This is the statement. This is the statement of Ampere-Circuital law. And this is a solid wire. It's a solid cylindrical conductor. So for a point inside the cylinder, what I understand is R is less than R. And I need to calculate this I enclosed that has been flowing through this wire or through this cross-sectional area. Now I understand that the total current is I, which is being flown by the pi r square area. So this is a smaller radius. Let's have a look very closely. So current from area pi r square, it's a pi into small r square, is, we can write it's an 1 by I by pi r square multiplied by pi r square. You understand this, and this is I into r square by r square. So now according to the Ampere-Circuital law, it's a B into 2 pi r should be is equals to mu naught times of I dash, and that I dash can be replaced by I into small r square divided by capital R square. So this is equals to mu naught into I into small r square divided by capital R square, and that can be replaced, that can be rearranged something like that. B inside is equals to mu naught times of I into R divided by 2 pi r square. Even this will represent that this is the distance from the axis of the cylinder, that B inside is directly proportional to the distance from the cylinder. Yes, so as soon as you are moving from the axis to the surface, magnetic field will be increasing. I hope these things are clear. Is it clear? Great. Let's look at the magnetic field for the point 2 and point 3, and we are going to discuss their geometrical representation. Let's have a look. It's a magnetic field due to infinite long solid cylindrical conductor. We are continuing this, and now we are going to look at this point, a point 2 on the surface, and we are going to look at this point. It's a point 3 which is outside the cylinder. So for a point on the surface of a cylinder, by Ampere's circuital law for circular path, it's a B on the surface which is equals to 2 pi r. That should be is equals to mu naught times of I enclosed, and B on the surface should be equals to mu naught I by 2 pi r. Yes, it is the maximum possible. Yes, it is the maximum possible. Now let's look for the third point. It is for a point outside the cylinder. It is for the point which is outside the cylinder. So if I look at this, again doing the same thing, it's a B out into 2 pi r, but now the dl should be consideration of this. So this is the line integral of dl, which should be 2 pi r. I hope you understand this. Yes, so it's a B outside multiplied by 2 pi r should be is equals to mu naught times of I enclosed, and this B out, it's a B on the outside, should be is equals to mu naught I by 2 pi r, and this is inversely proportional. This is B outside, A is inversely proportional to the 1 by r. Is it clear? So if I understood well that if I plot a graph forces B versus distance, it's a magnetic field versus distance, while I calculate the distance from the axis of a cylinder, what I understand is at 0 magnetic field will be a 0. From 0 to radius r, I need to use relation of the inside magnetic field. Even we have performed this kind of thing in electric charge and fields as well as potentials. Yes, we have gone through this kind of applications, but we need to understand and we need to focus on it that within the when we were inside the cylindrical, or I should say solid cylindrical conductor, magnetic field is directly proportional to the r, and when we are leaving it, that means when we are on the surface, it is the maximum possible, and when we are moving outside from the cylindrical conductor, it is starting decreasing according to the relation 1 by r. Yes, so this would be the plot for the magnetic field versus distance r. Any doubts or any queries in this? Anything? Is there anything? Yes? No? Great. So now let's work for the next. It's a magnetic field. It's a magnetic field due to infinite long hollow cylindrical conductor. Yes, difference it was the solid cylindrical conductor. Now it's a hollow cylindrical conductor, and the current I has been flowing through axis of the cylinder. So again we have chosen the 3 points: 1 inside, 2nd on the surface, 3rd outside the surface. So for a point at a distance r such that which is at A less than r less than B. Yes, we have considered two surfaces. One is the inner surface, and the radius of inner surface is A, and the radius of outer surface has been considered as a B. So I need to write down it's a B multiplied by 2 pi r, it's a line integral of B dl I'm talking about. Yes, is equals to mu naught times of I enclosed. Now I enclosed could be written as r square minus a square divided by b square minus a square, that we have done in the last time as well. So now when we understood that I'm talking about the inner surface, this I dash could be written as, let's have a look clearly, it's I into bracket r is equals to a, it's an a square minus a square upon b square minus a square. So this a square minus a square make them 0, and this I enclosed would be 0. So if I enclosed is 0, this is something like this. It's a mu naught times of 0, and that's why B inside is 0. We are talking about the hollow cylindrical conductor. Yes, when we are talking about the outer surface, that means probably on point 2. Yes, it would be. It would be B on the outward surface. It would be a mu naught I by 2 pi b. That is the maximum. It was the same as we have derived for the solid cylindrical conductor as well. I hope this is clear. Is it clear? Great. And now let's look. Let's look for a point at a distance r such that r is greater than b greater than a. That means we are talking about the third point, which is outside it. It's a it's a line integral of b dl is equals to mu naught times of I enclosed. So this is b3 into 2 pi r should be is equals to mu naught into I, and this b3 is equals to mu naught I by 2 pi r. On a point on the axis of the cylinder that you understand, at that point distance would be a 0. A distance would be a 0, that was b on the axis would be 0. So if I plot this situation for b versus r, if I plot this for this situation, it's a b versus r, then I understand that from 0, that means from the center to the surface, magnetic field will be a 0, and it is something like this. And as you reach the surface, it would be a maximum. Yes, if you reach at the surface, this is maximum, which is equals to mu naught I by 2 pi r. And from there onwards, as you are moving away, from the cylinder, yes, it is decreasing. I hope this is clear. So up till now we have derived the relations. For three things. Let's just summarize this, and we will move towards the numericals. So it's a summary for straight wire, hollow cylindrical conductor, and solid cylindrical conductor. Yes, we are interested in the summary of these three people. First, it's a straight wire at this point. Let's understood that this is at distance r, the current is I, then we can understood that this would be B is equals to mu naught I by 2 pi r. This was first. Now second, it's a hollow cylindrical conductor. So it's a hollow cylindrical conductor, and this is its axis. We are interested in primarily 3 points. This is first, this is second, and this is third. So for the B1, which is B inside also, it's a 0. Yes, why? Because I enclosed equals to 0. On the second point, on the surface, you can write like this, it's r less than r. This is r equals to r. This is equals to mu naught I by 2 pi r. And for the third point, it's a mu naught I by 2 pi r, where r is greater than r. Yes, this all are the distances that you understand very well now. Yes, this is up to here. Yes, so long cylindrical, hollow cylindrical conductor, and for the straight wire. Is it clear? Now let's work for the third case. Third case, it is the solid cylindrical conductor. Yes, it has been filled. This has been completely filled, and this is the axis of the conductor through which current is flowing. This is the first point. This is the second point, This is the third point. For the first point where r is less than r, you need to consider it's b multiplied by 2 pi r should be is equals to mu naught times of I dash. And how could I find out the I dash? How could I find out the I dash? I understood that for the pi r square, the current would be I. For the pi into smaller r square, it would be an I dash. So I dash should be is equals to pi r square multiplied by I divided by pi into r square. It would be something like this. So this is equals to mu naught multiplied by I into r square divided by r square. This is equals to b inside multiplied by 2 pi r. Yes, I have derived this so that if you have forgotten it, you can easily derive it. This r can be cancelled, and this b inside could be written as mu naught into I by 2 pi into r square multiplied by r. This is, please do remember this. This b is directly proportional to the r. Second point on the surface. It's a b on the surface, which is r is equals to r. This could be written as mu naught I by 2 pi r. This is the maximum possible. And for the third location, it's a b on the outside, which is r greater than r. It would be an mu naught I by 2 pi r. I hope those things are clear. Is it clear? Is it? Are you sure? Have you written this? Yes? No? No? Okay. Do one thing. Yes. Note this down. Please note down only the formulas. Yes, because we are going to receive this class notes. So there is no need to write down the complete things. Yes, you will be having the class notes. You will be having an access of it, and you can make your class notes. But at this point of time, just note down the formula so that you can go through the numericals that we are going to discuss. Do it fast. Have you written it? Have you written it? Are you sure? Great. Also write down this. Yes, go for the formulas only. Yes, this, and this. Only these three things. Have you did it? Have you done? Have you? Great. So, ready for the questions? Let's have a look. Suppose a straight conductor is given, and this is having a current of I1. Then this is a solid cylinder, and current that is flowing in the same direction, it is I2. Actually, it is flowing through the axial part, but I have represented it on the outer side so that the things would be a clearer. And it's a hollow cylinder, and the current has been flowing through it is I3. What you need to do is that we have few locations, such as this is the point A, even it is the distance, and this is the point C. Yes, what do you want? You want that find out magnetic field at point A and point C. This is your requirement. Find out magnetic field at point A and point at point C. This is your requirement. How will you do this? So what I understood is that at point A, which all were there, who is going to contribute the magnetic field? First is the straight wire. So let's write down the magnetic field. We are writing out that magnetic field at point A. So it's a magnetic field at point A. So for the straight wire, it is a B1. It's a mu naught I1 divide by 2 pi A. Next magnetic field due to a solid cylinder, and it would be a B2. It would be equals to, that would be equals to mu naught I2 divide by, as you can see this, for the solid cylinder, this point is outside the cylinder, and when it is the outside the cylinder, my standard relation was mu naught I by 2 pi r. Yes, then the I could be written as A. So it's a mu naught I2 divide by 2 pi A. And the third one is for the hollow cylinder. It's a B3. Again, this point for hollow cylinder, this point is inside the cylinder, and for hollow cylinder, a point which is inside, the magnetic field will be a 0. So when I go for the B net, it would be an B1 plus B2. No need to write B3 as it is already 0. So this is equals to mu naught by 2 pi A into bracket I1 plus I2. I hope these things are clear. Is it clear? Is it clear? Great. Now on the next question, you need to find out the magnetic field at point C. You need to find out the magnetic field at point C. How will you do it? If you understand it carefully, that for the I1, this is at distance C. For the I2, this is the outside. For the I3, this is the outside. And always you are going to calculate the distance. Always you are going to calculate the distance from the axial point. That means what you need to do is write down the magnetic field due to first wire. The distance is mu naught I1 divided by 2 pi C. Go for the B2, magnetic field due to second wire. It's a mu naught I2. Yes, this is the second wire. It's a solid cylinder, and for this is the outside the point. It's a mu naught into I2 divided by 2 pi C. And the third wire, it's a hollow cylinder. For the hollow cylinder, this is even the outside, and if it is outside, this B3 could be written as mu naught into I3 divided by 2 pi C. Yes, so if I go for the B net, then B net could be written as B1 plus B2 plus B3. That should be is equals to mu naught by 2 pi C into bracket I1 plus I2 plus I3. This is the net magnetic field. This is the net magnetic field. I hope this is clear. Is it clear? Is it? Are you sure? Great. Done. What was your answer? Is it the same? Is it? Great. So let's work for the one more question. Do it fast. You are doing a good thing. So in this situation, let's suppose it's a straight wire. A current I1 is flowing through it, and let's assume that this is a cylindrical sections of another wire. A current I2 is flowing through it. Yes, what do you need to find out? Yes, this is the hollow cylinder. This is the hollow cylinder. Yes, one more solid cylinder is there, and current through this is the I3. Yes, now from the axis one of the point is there, and this point is at distance r. This point is at distance r. So what you need to do is that find out magnetic field at point P, which is at distance r from the axis. You need to find out this. You need to find out a magnetic field at a point P, which is at distance r from the axis. So what you need to do is you need to write down the magnetic field due to each one everyone. So let's do it quickly. First, it's a B1, which should be is equals to mu naught I1 divided by 2 pi r. Yes, for everyone this point is outside. For everyone this point is outside. So it's a B2. It's a mu naught into I2. Mu naught into I2 divided by 2 pi r. For the third one, it's a B3, which should be is equals to mu naught into I3 divided by 2 pi r. So we have written the magnitude. Now it's a time for the directions. So it's a B net. It's a B net. Now let's suppose understood that this the situation is that this is moving in positive x direction. Even I3 is moving in the positive x direction and I2 is moving in negative x direction. So magnetic field due to I1 and I3 would be in the same direction. How could I come to know? According to the right hand rules. Yes, and magnetic field due to I2 would be in the opposite direction. So what I need to do is that I need to add this two. It's an I1 and I3. It's a B1 plus B3. Let's assume that this would be the positive, and I need to subtract this B2. So that should be written as mu naught divided by 2 pi r into bracket I1 plus I3 minus of I2. I hope these things are clear. Is it clear? Is it? Any doubts on this? Anything? Any doubts? No? Great. So let's just wind it up this session over here. Yes, this was the part 1 of the Ampere circuital law. We have still left with certain applications of Ampere circuital law. Yes, that we are going to cover in the second part of this session. Yes, but before you tune into that, please revise it very carefully. Try solving this kind of questions based on the wires and cylinders. I hope this is clear. So please do it. That will help us to get it done. Thank you. Have a good day. Take care.